class website for sure, and then we shall do attendance. I didn't just stop the projector. Alright, so tell me that you're here, please. And then we can get going. So I am going to release your next programming assignment today because you have one due. So just like the essay last time. So let's try and make sure I don't forget that. That's important. I don't think I have the world's longest amount of slides left. We're just going to finish up these today, and then you can work on whatever you need to work on. So I want to get into, I want to come full circle. We want to be able to translate English, some argument, something that we want to be true, to very precise math. That's what we were trying to do last time. And then actually there's a third side of this, I don't know, logical triangle, I guess, where we can take that math and prove a theorem. We can prove that our mathematical precise statement is true using a program, actually. We can write a program and let it be a proof. It will prove our theorem for whatever we were trying to show. That is coming full circle to computer science. All right. And so I want to start with just some definitions. Let's start with what a predicate is, okay? This is going to get us almost all the way there. So a predicate is a proposition with some variables in it. So let's go back to these terms. So a proposition is just anything that's true or false. So let's define that. A proposition is something that is true or false. And so this is just a new term. A predicate is a proposition with some variables in it. So like a proposition would be something that's true or false, like it's raining today. That's either true or false, right? That's just a normal proposition. And even though it's gray outside, it looks like this is a false proposition, okay? So let's make it a predicate now. How do we make a predicate? We just need that proposition with a variable in it. It's like a function involving something. So here is an example predicate. I'll call it P. It takes like some X, and then it becomes a proposition once you give it that variable, okay? So let's define P of X to be X has a cat. Okay, this is a predicate. Do we see the difference? Like, this is not yet true or false until I tell you what X is, right? It could be true or false depending on whether you plug in me to P, because I do have a cat, or one of you who does not have a cat. Maybe you have a dog instead, okay? So you have to give it something before it becomes a proposition. A predicate is like almost a proposition. So it's one with some variables in it. So you can plug me into P of Lawton. That is totally true. But maybe P of somebody else is false. Okay? So it's all about that variable. That's what a predicate means. All right? And the reason I'm going here is because every time we used a for all or there exists quantifier, we had to add a variable. Okay? And so that kind of naturally makes a predicate. So I could say something like this now. For all x, P of x. In this, using this P, it means the following. It means, well, for every x, P of x is true. That's what it's trying to say. And so if P of x is x has a cat, this is saying that everyone has a cat. It's asserting that idea. Everyone has a cat. For every value of x, P of x is true. You see how I'm reading that? You see how this says, it translates the English, everyone has a cat, to logic. Are there any questions about that? That's a big jump, I think. But it's necessary. It's a good way to be able to express these ideas in mathematics, which is fun. All right, if we're happy with that, let's keep on trucking, because now we need to, how do we come up with these predicates? How do we come up with these ideas so that we can say exactly what we're thinking precisely in math, and then go and prove that what we're trying to say is true? Okay? That is our end goal. So here's my first silly example. Example 1. There is a prime number that is greater than 50. Okay? So trying to go into predicate land with this, let's call this special number that we're thinking of, this prime number that's greater than 50, call it x. And we should ask ourselves now, what is true about this x? Okay? So does anybody have a good idea? What should we say is true about this number x when we're associating it with this English text? What is true about our number x that we're trying to prove this about? Yeah, it's greater than 50. That's one of the pieces of this, right? That's one of the pieces of this thing that we're trying to show. So yeah, there's two things true about it, right? Exactly what we were saying. It's just take this, make it slightly more mathy, I guess. But now we've given a name to the thing that we're trying to talk about. That's important. We got to give it a name, okay? So we say x is greater than 50 and x is prime. Those are the two things that are true about this x, okay? The special prime number that's greater than 50. That's a nice change of perspective, and that will help. And what is this but a predicate? Isn't it? It's not yet true or false because we haven't said what x is. Oh, okay. We can keep going. We can translate this to more math, right? We know what and means. That's a logical quantifier. So we can use our and symbol. We could also say this, prime x. What is this? But also a predicate. It's a little mini predicate within a predicate. It's saying whatever you're giving, it's asserting that it's prime, okay? Itself. A predicate. Isn't that neat? So, like, prime of, I don't know, 5 is true, but prime of 6 is false. Those are predicates. It's not yet a proposition. It's not yet true or false. It depends on what you plug into. So you can build up bigger predicates from smaller ones. Isn't that neat? So that's useful. Okay. And so our goal is to prove this idea. There is a prime number that's greater than 50. We got it down to this form, which is looking more mathy. And our goal is to prove that this is true. That there is some x for which this holds, right? If we can just find it, right? If we can find some x, and s dot t dot stands for such that. I think I didn't spell it out before, but that's what it means, such that. If we can find some x such that this above idea is true, then the whole statement was true, right? And what quantifier do you think I need over x? Should it be this one or this one? Do you remember their names? I want to find some x such that this is true. Am I talking about every possible value of x? Or am I talking about potentially just one? Yeah, it's just one. There exists. There exists an x. There is. There is or there exists. That's what we need here. There exists an x such that x is greater than 50 and x is prime. Yes? That is the final mathematical statement that we can then go and prove true or false. That is what we wanted to get to. Okay, that's this in math. This English, we have converted it successfully now to math. This is our little theorem statement. There exists an x such that x is greater than 50 and it's prime. And now we want to go and prove that, right? And I think that we can all agree that there is some number greater than 50 that is prime. It is a true statement, right? This is a true statement. And what do you know? If this is something that could be true or false, that means it's a proposition. So by using this quantifier, we have taken this from predicate land to true or false land, proposition land. Did that jump make sense? I know this is getting a bit technical. But this is precise math now that we can go and maybe prove that it really was true somehow. Yeah? That's our goal. And so that quantifier helped us out. It gave us something that we could then go and prove true or false. Whereas this was kind of not ready. It was a predicate, right? It was not something that we could prove true or false yet. But by introducing this quantifier over x, that helped us. Okay? So here's our key idea at the bottom here. Every time you use a quantifier, it introduces a variable. It's like, okay, this thing is true for some x. This thing is true for every x. It allows you to introduce a variable, and it lets you go from a predicate all the way to a proposition, because it quantifies over that variable in a certain way. It's like it's true for just one thing, or it's true for every possible thing that you could plug in. Okay? So that was a lot of words, a lot of symbols. Are there any questions before I move on and talk about how to prove this statement now? Now that we've worked so hard to get to this form, I want to prove it next. But I want to make sure we understood how we got here. All right. So now our job is to prove this true or false, right? Let's do that. What does that mean? Well, if this is true, right, that means, okay, there is some number, call it x, that's greater than 50 and it's prime. We could find that, right? If we just found that prime number, if we found some prime number that's greater than 50, that could be our x, and then it would have been a true statement, right? So let's find that number. What better way to find it than to write a program to search for it? Do you see how a program could be a proof? That's pretty cool. So yeah, we can program this now. We can write a program to find that special x. And let's talk about the strategy involved. What's the algorithm that's going to find us this prime number that's greater than 50? Okay. Let's assume that we have an isPrime function that gives back true or false based on the number that we give it. So we'll make that too, don't worry. But let's pretend we have one. It's like you give it a number, isPrime of 42. That's just false, right? That should give back false if it's not prime, and true if it's prime. But that is our idea. So what do we want to do? How can we find? Do we have any ideas about how we might go about finding a prime number that's greater than 50? Assuming we had this isPrime function that we could call and use to tell us whether or not we found a number that was prime. Any thoughts? Because this is what we want. If we could find that number, we would have proven this statement. We would have proven it true because we did find a number that's greater than 50 that's prime. Okay? So how could we in code figure out, here's a prime number, it's greater than 50. How can we find one? We don't know where it is. Yeah. Very nice. So if we're not sure where this thing is, we know we need to find a number that's greater than 50 that's prime. Well, let's start looking at 51. I'm not sure if that's prime. Actually, no, this is divisible by 3, isn't it? So 51's not prime. That's okay. We can just keep checking. Let's try 52. Let's try 53. ... Let's just keep using numbers, starting at 51, going forward by incrementing by 1 at a time, right? Until we find a number for which isPrime gives back true. Does that strategy make sense? Because that will prove our original theorem. It will find that number, and then that means this thing that we were trying to do, yeah, it was a true statement. There is an x that's greater than 50 and is prime. That's an algorithm to find what we're looking for. Okay, so here's like the code, but not really. It's like English-looking code. It's called Pseudo Code for this idea. Whee! And so here's what we'll do. We'll iterate through all the numbers with a while loop starting at 51. So like we'll use the variable I to keep track of where we are. It's like, okay, start I at 51. And then keep on checking, hey, is our current value of I prime? If so, we're done. We found that number. Yeah? Otherwise, increment it. Otherwise, make it 52, then come back to this loop, right? See if this one's prime now. Oh no, if it still isn't, let's increment. Make it 53, ... until I is prime. Once it is, be like, hey, I found a prime number, and because I started at 51, I know it's greater than 50, so I just proved your theorem. So a very powerful thing that will come up later if you go further into computer science is there is a very, very precise way of proving something using a program. A program is essentially equivalent to a proof, actually, believe it or not. It's a very powerful idea that I don't think we're ready for just yet in this class, but it's a very, very fun thing that I can at least give you a hint at right now. Okay, so here's our code. We can just program this, and we'll find some number eventually is prime, right? That is greater than 50, and that will prove our theorem, right? And I'll prove this theorem. Yes, it's true. Okay, so that's my goal. Are we ready to actually get out to Python and program this? All right. So I'm going to open up idle. Feel free to follow along. But I'm going to translate this pseudocode to real Python. After I make a folder for today, of course. So let's figure out what lecture we're in. We are apparently in lecture 21. Let's see, it's on my desktop. All right, let's call this prime greater than 50.py. All right, so here's my goal. Here's what I want to do. Let's try and give us some room. So here's this. I would like to implement this idea right here. There we go. So I want to go through all the numbers, call them I, starting at 51. So how do I do that? It's just a loop. So start I at 51, and then, I don't know, we could just make this a forever loop, right? Just keep trying forever and ever until I stop you, okay? While true, just repeatedly check if I is prime. If it is, then print it out and stop the program, because that will prove our theorem. Otherwise, keep checking. Increment I, so that we check the next number, the next possibility, in the next iteration of this loop. All right, so that's what I want to do. So check if I is prime. Let's assume that we have this is prime function that gives back true or false. So if is prime of I is true, then, yes it is, we found a prime number. Hey, that was greater than 50 because we started at 51. Let's print it out. So we can say print I, and that will print our answer, the x value that we finally found. That will prove our original theorem. And then also, this is an infinite loop right now. We'd like to stop it because we found our one value. We don't have to continue forever. The way to stop a program, there's a quit function in Python. So this, if I just say this like this, it will stop the program. Okay, that's what that does. Otherwise, if we didn't hit this if statement, we didn't stop, right? So we keep on going down here in the body of the loop. And if that's true, then we should increment our I variable so that the next time we come back to this loop, because we're never going to stop until we quit, right? Then I is 52, or I is 53, I is 54. Forever and ever and ever until we find an I that's prime. Okay? Any questions about that? Does that seem like a good translation of these words down here? All right, the last thing we need to do is check if a number is prime. So this function does not exist right now. So I'm going to secretly make it. You can like shield your eyes if you'd like, because I haven't told you how to make a function yet. But I'm going to make it for you right now. Feel free to watch if you'd like. So what does it mean to check if a number is prime? Well, let's talk about that just briefly. Let's see. A number let's call it n. A number n is prime when what's true, right? What does it mean to be a prime number? It means it has no factors other than it and 1, right? So a number is prime, call it n, when you try to divide 2 into it, you try to divide 3 into it, you try to divide all the numbers between 2 and n minus 1, and none of them go into it, right? None of those are factors, right? When none of those numbers don't, when all those numbers don't divide, let's say cleanly, into n. Okay, so that's one definition of a prime number, and that will give us an algorithm to see if a number is prime. So I'm going to make a function right now. You don't have to understand what I'm about to write, but at least try and pick out the places where I'm looking for these ideas. Like I'm trying to try all these numbers, right, between 2 and n minus 1, and see if they divide cleanly into n. Okay? All right, so here is my isPrime function. Feel free to look away. So here's how you define a function. I'll teach you this later. Def is prime of some number n. So I need to try to divide n by 2, 3, dot, 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 all the way to n minus 1. So I'm going to loop. And again, I'm going to go fast because I don't expect you to understand this right now. So let's try, I don't know, let's use j or something. Start j at 2. While j is less than or equal to n minus 1, because those are the numbers, like that's the starting value of j, that's the ending value of j that I want to try. Let's keep on checking. So try to divide by this. So how do you divide by something and check and see if it divided cleanly? You can get the remainder. Do you remember that? So for example, you can check to see if 42 divides cleanly by 2 if you get the remainder, 42 mod 2. What's left over? If nothing is left over, that means it divided cleanly into the number, okay? 42 divided by 2 apparently goes in 24 mod 12, for example. 12 goes in cleanly to 24. There's nothing left over when you get the remainder. That's the trick, okay? So try to divide n by j here, because I'm trying a bunch of different values of j that range over all these numbers. And if n mod j is 0, that means it was cleanly dividing into n, and that means j is a factor, which then means that this was not a prime number. Return false. So we give back the number, the idea that this is not true, right? It's not a prime number because I found something that divides into it. Again, I'll teach you what return means, don't worry. And so we've tried all these numbers. Eventually, if we ever get here, we've tried all the possibilities and we never said no. We never said, hey, I found a factor. So that means there weren't any. That means it must have been prime. We give back true. So that's my silly isPrime function. You don't have to understand any of it, but that's the idea. Are there any questions about this complete program now before I try and run it? I'm just using this isPrime function to check. All right. Oh, sorry. As we're iterating, of course, I need to try multiple different values of j. So j equals j plus 1 down here. My bad. So let's see here. Yeah, I think that should do it. Let's try it. Yay! Sure. That was quit for you. And look, it's printing 53. Apparently 53 is a prime number. That's the first prime number greater than 50. And then I'm calling quit, and so it's like, your program is still running. Do you want to stop it? Sure. All right, so it found it. It found the number, it printed it out, and it stopped the program. 53. That's the number that it found. That was prime, that was greater than 50. We wrote a program to prove that this statement is true. We've come full circle. Any questions about this? That was a long process. But we did it. Go us. All right, I have another example. Let's see here. Yeah. Here's our next theorem that I'd like to show that we can prove with a program. Let's prove that for all integers n between 0 and 100, yeah, for all those values of n, the square root of n is less than or equal to 10, right? And that makes sense, right? Because here's the graph of square root. It starts here. The square root of 100 is exactly 10, right? So it's always, everybody before it was strictly less than, right? So this is a true statement. It's a true theorem. We just need to prove it now. So the trick, the way you do it, the way we prove this is we first convert it to math, right? Slowly but surely. We get a mathematical statement out of this, and then we can program something that will prove that precise math, okay? So here is the mathematical translation, almost mathematical translation of this idea. Prove that for all integers n between 0 and 100, the square root of n is less than or equal to 10. So here's how you kind of prove that. You have to add an if-then statement kind of idea. So if, give me a number, call it n. If that number is greater than or equal to 0 and it's less than or equal to 100, that's the range that we care about, right? Then the square root of n is less than or equal to 10. You see how this gets translated into this? That looks a bit more like math now. Because we have an if-then in math, don't we? That's an implication. So let's keep on going. And we know how to convert and. The rest of these are just comparisons. That's already math. So let's keep on going. We're almost there. So here's like our full-blown mathematical statement, right? So if, remember that the if-then is made up of this implication. That is a mathematical if-then statement. So if the thing on the left is true, if the hypothesis is true, then the conclusion must be true. Okay? So that's what our if-then gets translated into. And then, what is this but a predicate, right? I haven't told you what's true. Like, this is not yet true or false because I haven't told you what n is, right? You plug n being like 101, and it's like the hypothesis is false, so it's automatically true, right? Something like that. But it depends on the value of n, whether or not this is a true or false statement. If you plug n to be like 100, for example, yeah, it's between this is true, and this is also true. Square root of 100 is less than or equal to 10. That's perfect. Okay, so this is now a predicate. We need to convert this into a proposition because only that can be proven true or false. Okay, so that's our last step. So we got to add in a quantifier to create a proposition out of the predicate. So we need to quantify over n, right? For all integers n between 0 and 100, this is true. So you know which quantifier we're adding, right? I just spelled it out. That's the statement we need to prove now. Okay, for all values of n, if this is true about n, if it's within this range, then this must be true about its square root. Okay? Did everybody follow that? That's this English sentence converted to full-blown, perfectly logical and precise math. And this is what we now can go and prove. Try and prove at least. Any questions about that process? All right. So if we were to pronounce this now in English, it doesn't sound exactly like this because it's more precise. Oops. But this is how you might pronounce this in English now. So for all n, if, this is true, right? If n is greater than or equal to 0, or equal to, I guess. If n is greater than or equal to 0, and n is also less than or equal to 100, then the square root of n is less than or equal to 10. Okay? That is the precise statement that removes any possible ambiguities about this. This is what we need to prove now. Okay? Any questions before we try and prove it? All right, because I'm throwing this off to you. It's your turn now. So get together with your group and try writing a program to prove that this formula, this logical statement, is true. How would you do it? If you're not sure about how to write the program itself, at least write the pseudocode. Like, how would you discover that this is true or false? Okay? That algorithm is very important. Okay, so I'm going to give you, I'll put this code right here for you to look at. You don't need to see is prime. But here's the thing that we did last time. That might be helpful to you. Take a few minutes, I'll give you plenty of time, to write a program that checks to see if this is true. Remember that the square root exists in the math library. So if you say import math, you can say stuff like math.square root of 2. That's how you use the square root. That already exists. Okay? The rest is loops and if statements and things like that. So see if you can figure out as a group how you might prove this theorem. Because it is true, right? It should be true. How can you discover that with a program? So take a while, make a program, and ask me questions. Okay? We got plenty of time for this. Because it is a search process, right? You're going to search for this value that we're looking for. What do you need to search through? And actually, I wonder if I could show you any of the is prime, because that might be helpful. I guess not. Darn. There. So how would you show that this is true? Alternatively, think about what it would mean for it to be false. Like, say that the range was instead like 0 to 110. That would be true, right? How would you discover whether it's true or false? Shout out if you have a question. We got plenty of time to try this. All right, take about 2 more minutes to give it a good try, and then I'll do it the way that I am thinking. All right, that is my timer. Let's see how we might do this. So, does anybody have any good ideas that they'd like to share? How'd you come up with this answer? I'm gonna need a new file though. Square root proof, I guess. .py. So, let me tell you the way that I might think about this. So, I want to prove this theorem, right? For all n, if n is greater than or equal to 0, n is less than or equal to 100, then this must be true about that n. Square root is less than or equal to 10. Well, here's the pseudocode that I would try. So I only care if the number is between 0 and 100, right? So how about I just check every possible value between 0 and 100, call it I or something. I is 0, let it be 1, 2, all the way down to 100, so loop, and then make sure each time I have a different value of I that its square root is within this range, right? Try the square root of 0 when I is 0. Make sure that that is less than or equal to 10. Try the square root of 1 when I is 1. Make sure that that's less than or equal to 10, right? And then finally, at the very end, try the square root of 100. Make sure that that is less than or equal to 10. Do you see how that will prove the statement? It's like, yeah, I've tried all the integers between 0 and 100, and I've made sure that their square root is always less than or equal to 10. So that will prove this entire theorem. If this is true, yeah, I tried every possible n, then this must be also true. I have confirmed that for each case, for each value of n, it doesn't do anything weird, it stays below 10. Okay? So that's the idea. So loop through every number between 0 and 100. I guess we can call it n this time instead of I. It doesn't matter. And then if the square root of n is greater than 10, that's when it went wrong, right? That's the trick. So you kind of think about it in the opposite way. So what could go wrong? Well, the square root of n, we better make sure that it is less than or equal to 10. If it's never if it's ever greater than 10, right, if ever the opposite is true, then that disproved our statement. That disproved our theorem because we found something bigger. So if this ever happens, then we can immediately stop and be like, oh, nope, this special value, it doesn't work out. Otherwise, if we got through this entire loop of checking to see if we ever were too big, if we got through that entire loop without ever printing false, then we can print true. Because that means we tried every value. They were always less than or equal to 10. We're good to go. Do you see how this idea would prove the theorem? Is that what we came up with? Any questions about that? All right, because that is the answer. That's how we do it. So, let's see here. Loop through every number n between 0 and 100. So instead of I this time, I'll use n. So start n at 0, and then keep on looping while n is less than or equal to 100. And then to advance the loop, it's always n equals n plus 1. Okay. And then for each value of n, we want to make sure n, the square root of n, is less than or equal to 10, right? So if it's ever not, if, I got to import math, right? If the square root of n is ever greater than 10, that means I found a counterexample. That's the fancy word for this. If that's the case, then that means it's not true, okay? That means, uh-oh, we found something that doesn't prove the theorem. So print, I don't know, false. The theorem is false. Okay? And then we can stop the program, maybe. Because that is set. Otherwise, right? Otherwise, if that's not true, keep on trying. If you're within the range between 0 to 100, keep on trying a new value of n, because we got to try all of them. All of them between 0 and 100, right? Get ready to try the next n. All right? If we ever got through the entire loop without completing and stopping the program, so if we ever get here, that means we didn't go to this body. And that means we didn't print false, because we would have stopped the program by now, right? If we ever get here, that means we tried every value, and it really was less than or equal to 10 every time, because this was never a true statement. Okay? If we ever get here, the theorem was true. All right, so we can print true. And that is how to convert our, or how to prove our mathematical statement with code. So let's run this, see if it's going to work. And so we tried every value. We gave it all the numbers between 0 and 100 a chance to be n plus plus, or n plus 1, n equals n plus 1, n equals n plus 1. We made sure that it was within the right range, and then, yeah, we never complained, so we print true. It's a true theorem. Yay. If I changed this statement to be a false statement, if we proved between all the numbers between like 0 and 101 that the square root is less than or equal to 10, that's no longer a true statement, right? This should also notice that, right? This code should also notice that. If we did this, okay? If we made it a false statement, we tried 101 as well, then for 101, it would notice that it's bigger than 10, right? And so it's false. Stops the program. Does that make sense? That's how we can do that. So let's go back to normal, at least. But that is the idea. Are there any questions about why this code proves the theorem? All right, so yeah, we just tried all the numbers, checked, and saw if any of them are greater than 10, then something went wrong. So yeah, that's my last example that I have for us today. So the moral of this story is there's a very deep connection between logic and computer science. Programs can be proofs even. It's amazing. So consider them together. using logic with computer science sprinkled in. It helps you write correct programs because we're thinking at the very beginning about, okay, we need to prove a theorem. We need to write a program that's going to do this thing. So it'll help you be a better programmer, and it will help you argue why existing programs are or are not correct, because we're getting practice with noticing, okay, what could go wrong? What should be happening? So we love to be able to write correct programs. So use logic as a programmer, and your life will be much better. Okay, that's the moral of this story. And yeah, the last thing that I want to do is show you your next programming assignment. And that's all I got for you. So let me release that. Let's make sure I'm logged in. Let's refresh the page. Okay, good. We are here. So here's programming assignment 7. Also do week 14 like your essay. So here's what I want you to do. It's very similar to the program that I was writing in our previous programming lecture. So here's what I'd like you to do. I'd like you to do some more random stuff. Okay? So write a Python program that uses turtle and random to do the following. I would like you to ask the user to enter a number. For the rest of this instructions, I'll call it n, but you can call it whatever you want. So you ask the user for something, for a number, and then you're going to do the following n times, okay? Because the goal is to draw exactly as many things as the user asks for. So if the user types 42, you're going to draw 42 squares or triangles, okay? So it's all dependent on what the user types. So you need to ask the user for a number, using input, converting it to an int, things like that. And then do the following n times using a while loop. I've shown you how to do that last time. Go and look at that code that I posted. So here's what you need to do each time you try a new value. Okay, every time you iterate through this loop. I want you to set the current color that you're about to draw with to a random color. So this is going to let you draw random colors each time. So you can use as many colors as you'd like. You can use more than I did in my last example. So here's a long list of colors that Python knows about. There's a ton of them. So feel free to add all of these if you'd like. But these are their names that Python knows about. So pick a random color. Set the fill color for your turtle to be that. And then I would like you to randomly pick whether or not for this round to draw a square or a triangle. You're going to draw both, potentially. Randomly picking at each go, hey, I'm about to draw a square, or I'm about to draw a triangle. So you're going to randomly pick. You can use the random module to like flip a coin for yourself. Think about how you might do that, okay? So that means when your program's running, it's doing this thing n times. It should draw some squares and some triangles, because it's picking each time when it's in this loop, whether or not it's about to draw a square or it's about to draw a triangle. And the total number of shapes you're drawing, because you're doing this n times, is n, okay? And then you just do the normal stuff, randomly pick the size for your square/triangle, and then draw that square/triangle with that color at that random spot with that random size, okay? So you're drawing n shapes in total. And this is kind of what it looks like. You're doing a bunch of, like, maybe the user types 4 as the number, and then randomly each time you're like, okay, I'm going to draw a random triangle this time. It's going to be blue. Okay, next time I randomly pick, I'm going to draw a square. It's this big over here, and it's going to be, I don't know, horizontally lined. I don't have multiple colors right now. And then the next time, maybe you need to draw another square because you're randomly picking, and it's this color. And then finally, you draw one more triangle. So you're drawing 4, whatever the user gives you, that many shapes, and the color is random, the size is random, and the shape you're drawing is either a triangle or a square. You have to randomly pick each time. Okay, so this is kind of like what your output might look like. Are there any questions about that? That's a lot of rules, but it's mostly similar to pretty much exactly what I did last time. It's just, you're going to draw squares and triangles randomly this time. Any questions about that? So yeah, I did the square drawing, random stuff with random colors, so just reuse a lot of that, but add in triangles and randomly pick between squares and triangles. So lots of if statements are going to be in play here, and you're also going to be looping. Does that make enough sense? Any questions about that? What's got to go on? All right, yeah, so just remember to follow these rules, and you're good to go. So I think that's everything that I wanted to say. If there are no more questions, use the rest of the time to get started maybe, and ask me questions about stuff.